Good afternoon, everyone, and welcome to the 11th open webinar for the MERLIN research project. My name is Jan Senzemir, and my job is to facilitate this afternoon, take your questions. We are quite fortunate to have Dr. Hamish Moyer from the CBEC consultancy, the eco-engineering group. Dr. Moyer has worked for over several decades on sustainable approaches to river restoration. Specifically, he's worked in areas of salmonid physical habitat characterization, catchment management, fluvial geomorphology, in-stream ecology, interactions, and river engineering, both on a research and consultancy basis, and is going to speak to us this afternoon about river restoration. Please feel free at any time to put your questions in the chat. I will be copying them, and we will try to catch all questions at the end. And if I have your questions and your name, I'll be able to call on you more easily. So at any time, type a question in the chat and I'll be monitoring that. Dr. Moyer, thank you so much for coming. The floor is yours.
Thanks very much, Jan. Thanks for inviting me to do this talk. I'll share my screen right now to make sure I have the right talk open here. Okay. Right. Right, is that, I'm hoping everyone can see that. So yeah, this is the title of the talk I'm going to give. It's some experience that we've had over the last 13 years in the practical application of what's now called nature-based solutions, but we've in the past called it the process-based approach to river restoration and river management. So I'm going to give a few case studies about examples of river restoration across a range of degrees of practical constraint. And then if I have time to give a couple of slides on more practical river management works, more alternatives to more traditional river engineering that can be done with a nature-based approach. Like my talk outline is first a little summary of how we define the nature-based approach, nature-based solutions, and how we apply it, why we apply it. And then, as I said, to give 4 case studies of varying degrees of practical constraint in this type of work. And then at the end to give some examples of more sustainable approaches to river engineering and management. I'm going to have to just focus on one example, which is bank protection work that we often get asked to do. You know, what is the nature-based approach? Fundamentally, nature-based approach or nature-based solutions is working with rather than resisting physical processes in the river environment. This enables sustainable management of the entire river environment, and that's quite important in terms of the definition of the river. We don't think of the river just as the channel, the low flow channel. It includes the entire functional floodplain, and if one to consider, you know, in a holistic sense, the entire river catchment, the entire watershed. So we're looking at valley sides and headwaters and estuary areas as well. So often, you know, restoration at the entire catchment scale is just not feasible for various constraints that I'll go into, but we always need to try and apply the largest feasible practicable scales to deliver a nature-based type of solution. The approach recognises the natural capital in river environments, the intrinsic value of a natural environment for human life, and importantly provides improved resilience to climate change. That's a very important aspect of that, and the related benefits to biodiversity and given current climate conditions. Often these approaches are carbon neutral or carbon negative in that they store carbon. So we're utilizing natural materials, but also encouraging natural regeneration of vegetation back to a more natural state for a river environment. So, but we've got to be careful not to use this term nature-based approach or nature-based solutions as a greenwashing approach. There's a bit of a concern about that at the moment. So we don't want to be looking at this as a carbon accounting exercise. The fundamental approach is to provide resilience to climate change and improvement to biodiversity, and any carbon benefit there is just associated with that. It's not the actual objective of the work. And also increasingly, this type of approach is being approved or preferred by environmental regulators. They see the value of this more sustainable approach as opposed to more traditional approaches. There's still a bit of work to do to convince people, but importantly, some governments now are legislating that nature-based approaches, nature-based solutions should be adopted instead of more traditional engineering. And if you want to do some traditional engineering, you've got to justify why you're not applying a nature-based approach. It's a very good development in the way things are going. So the fundamental design approach is effectively, in terms of river restoration and management, is to reproduce natural physical processes as much as is practicable. Now, our company, CBEC, has been going for 13 years, and during that entire time, our tagline has been designing with nature. So we've always applied this approach anyway. And it's only recently that the nature-based solutions has become a popular term. So as much as practicable, we're letting the river do the work. The river is the best architect of its own stable form and the associated ecology. So we really want to take as much of a hands-off approach as we possibly can and acknowledge the effectiveness of the river in doing the work. And it's likely, doing it this way, we're likely to have a much more stable and sustainable environment. As I said before, significant benefit to climate change and more environmentally sensitive designs, and with potential for carbon capture. Also benefits for biodiversity as well as associated with that. But there's very different approaches. There's not a one-size-fits-all type of approach. There's very different approaches depending on the geomorphic physical setting of the environment. So it's very important, as I'll demonstrate, to do sufficient levels of assessment and design to come up with the appropriate approach for different physical environments. But there are significant constraints which I want to focus on in the talk, and I'm going to give 4 examples of projects with increasing degrees of constraints. So the constraints can be infrastructure, services, property, land use pressures such as agriculture, fragmented land ownership, lack of catchment scale management plans, unrealistic timescales. These are all constraints which I'll hopefully give a chance to give some examples of. So different environments have different constraints. This is an example of a rural project where we realigned a heavily managed river environment in an agricultural setting, and we sort of reinstated a more natural sinuous channel with connected and online and offline wetland areas. So there's constraints related to the agricultural environment there, but other types of project, like for instance, urban restoration projects, have different constraints, and typically more significant constraints for obvious reasons, being in an urban environment. But there's always still ways that we can produce a nature-based type of design that greatly improves the condition. You can see the benefit here. So there's always constraints, but those constraints are of different degrees and different types of constraints in different environments. So I like to sort of present the different modes of restoration or river management in this conceptual diagram here. So on the x-axis, we've got the potential for geomorphic work, so how dynamic the river system is, and on the y-axis, perceived degree of risk or degree of constraint. Now, if we have a relatively little degree of risk and constraint, and the river is quite dynamic, you can pretty much do nothing and the river will recover itself. But we're not really interested in that. We're practitioners of restoration. So the next mode up this continuum is what we call assisted recovery, where here we're removing the constraints to natural process. The river's still got a fair bit of potential for work, and there's relatively little degree of constraints. We just let the river evolve over time with these constraints removed. So we're reinstating natural process. But what's often more typical is that we have a bit more degree of risk or constraint. The river's maybe not quite so energetic, so we have to apply what we call initial conditions design, and this is giving the river an initial condition, an approximately correct condition that the river then takes and through natural process evolves into into an equilibrium condition over time. So we're giving the river a bit more of a specific push in the right direction and letting it evolve subsequently. Where there's the highest degree of risk, and this may or may not be a location with little potential for geomorphic work, but we apply a functional design approach where we're pretty much giving the river a finished design, and that's it. This is what we need to have. It needs to be fairly fixed in place because of the degree of risk. But that's not to say there's not a nature-based aspect to this. We've got to try and reproduce that design based on the type of channel that would exist naturally under the imposed physical conditions of the site, which is usually the flow regime and the slope of the site. So despite it being quite fixed and quite static, it will incorporate a nature-based approach in coming up with that design. So this is the area of active restoration. I want to give examples across this continuum here, 4 examples, and this are in sort of degrees of increasing design constraint. The examples are, and they're all in Scotland. I hope that's not a bad thing. The Altlorgie, which is in the Cairngorm Mountains. This is an example of assisted recovery, often referred to these days as stage 0. It's a type of restoration approach that's a term that's quite popular these days. So this is a site with very little constraint. But then moving up the scale, another example of assisted recovery, the River Nairn at Aberarder. Assisted recovery, but because of the degrees of constraint, it's got an element of the initial conditions design as well. But then further up the scale, a fully initial conditions design was the Eddleston Water in the Scottish borders. And then finally, a significant constraint was the Mains of Dice. It's a small stream near Aberdeen City in the east of Scotland, and it's an example of functional design. So I'll go through these 4 examples in turn. So the Altlorgie is an unusually constraint-free restoration site. Very simple land ownership. One estate owned the whole area, and very little infrastructure at risk. So pretty much everything was on the table in terms of applying the nature-based approach. So, and again, you could potentially call this the stage 0 type of approach to restoration. I can describe what stage 0 means later, but it's effectively the most pure version of the assisted recovery approach. The fundamental principle really is to let the river do most of the work after the constraints to physical process have been removed. So it's really kickstarting dynamic, geomorphic or physical activity. Now this happens during flood events. This change happens during high flow events. So this is a fairly iconic view from just downstream of the Altlorgie site. It's on the River Dullin that the Altlorgie flows into. This is it under sort of moderate flow, and this is it under flood flow. So this is a fairly extreme event, but we've had a number of fairly large events that have influenced the Altlorgie and has allowed us over time to see how the channels evolved in relation to these high flow events that are transporting sediment. So you can see how much sediment is being transported by the color of the water here in the second photograph. And that's the mechanism for change. That sediment transport is fundamental for these rivers to adjust or evolve into a more natural state. So that photograph was taken at this bridge here looking upstream on the Dullin, and here's the Altlorgie here coming in, joining the Dullin just upstream, and this is the study site here. Now, historically, there's old maps here from 1875 and 1982. The river had a naturally dynamic, multi-threaded character. This is the sort of what we call the reference state. This is the state of the river we're trying to return it to. But in the late 1980s or mid to late 1980s, the river was managed for agricultural purpose. It was canalized, pushed up against its valley side, and you'll also notice artificial drainage ditches running through the valley. So it was very significantly constrained. And this is what it looked like before we did the work. So these are the embankments that were put in. This material had been dredged from the channel and built up here. It's a very simplified channel morphology. Also, the river's completely disconnected from its floodplain. So despite quite a nice rural setting, quite an impacted river given that environment. So this is the approach we took, just the existing conditions, and this is during construction. You'll see the machine working in the background here. So what we did, we're just removing the constraints to natural process. So we're removing these embankments, and because this material had been taken from the channel, we're taking it back upstream and putting it back into the river at appropriate locations to kickstart sediment transfer process to begin this trajectory of recovery. And after a few years, the same site looks like this. So we've got a much more natural, if you compare it to the photograph here, the top photograph, a much more natural channel form that's reconnected with its floodplain, and there's also significant riparian regeneration also. And then more recently, the river's further changed, and you can see now that these dynamic processes have really kicked in, and whereas the river used to sort of come around here, this direction to the right, it now flows off on the other side. The river evolved, it changed its course through natural processes, now flowing through this wet woodland. So there's really incredible habitat and biodiversity gains as a result of this project, and also because it's not confined in its channel, there's also significant flood risk benefits to downstream areas. And this is another part of the site upstream. This is one important component I forgot to mention there. As well as putting gravel back into the system, we also put in large wood, so pretty much whole trees into the system. Now, large wood is a very important aspect of natural process in these types of environment, and you know, as part of the restoration design, we put some large wood directly into the channel to kickstart. They're real catalysts to geomorphic activity and channel evolution. So we put, here's a large wood structure going in here, and then after a couple of years, this is what the site looks like. So it's really moving back to its reference state of this wandering system. It's not completely recovered yet. You know, the riparian areas are recovering slowly with natural regen, and the channels becoming more diverse, but it's definitely improving in a significant way. And we've monitored this through repeat topographic surveys. So this is prior to the works going in. This is 2012. The flows from bottom to top here, and these red symbols represent where we put the large wood in. So a relatively simple channel form here in 2012. And then after some high flow events, we've resurveyed. So 2014, 2016 and 2019. So you see this gradual improvement in physical diversity. And you'll also notice that much of that change is proximal to the woods going in. The wood, the large wood input really provides a catalyst to change, and there are real hotspots of morphological evolution where the wood's gone in. So a very important component is the large wood as part of this assisted recovery type of approach. The next site, case study along this continuum, is the River Nairn at Aberarder. So again, assisted recovery, but there's a bit more constraint here that we have to consider. So this is about 10 kilometres south of Inverness, not too far from Loch Ness. So this is a river as it used to look, obviously heavily canalised and straightened, you know, very little biodiversity in the channel. Because there's a high supply of sediment from upstream, the bed of the river over time just aggraded. The bed of the river increased over time, so the elevation increased, which means they had to put embankments in to hold the river in place. And over time, the river ended up being about 2 meters higher than the elevation of its adjacent floodplain. So it's disconnected from its floodplain in a negative sense. And when it does flood, it creates very significant flooding issues, but also under normal flows, all the agriculture adjacent to the channel, the drainage was impaired because the drainage ditches couldn't drain into the river that was just too high elevation. So the idea here, here's the the straightened section here, it's over 1 kilometre long. So the idea here was to design a more sinuous channel. So it's a little bit of the initial conditions design, because we've got to give it this proto channel to work on, but we've really just dropped the river into this new orientation and let it evolve over time. So this section here, we put in a number of these large wood structures that I mentioned before, and then downstream the river gets dropped into these low areas. These are actually old historical meander bends. We just drop the river into there and they create really nice wetland ponded areas. I'll just focus on this red area at the moment. So this is this site under construction. You'll see this the sinuous channel being built, and these are the large wood structures. So they're orientated and located in places where wood would naturally accumulate in a river, so just downstream of the inside of a meander bend. And they tend to be alternate, they go from one bank to the other. this is the site as it was. Again, this is low flow conditions. They're very, very poor habitat conditions here under low flow conditions. Some are low flows. So the design approach was to implement large wood structures in combination with channel realignment for these benefits, mainly ecological, but also in a practical sense for sediment management and land drainage issues relating to agriculture. This is where the constraints come in. We have to consider these issues as well. This is the photograph I just showed of the channel as built. And this is it a couple of years after, and you can see the effect the large woods had. The roughness of the large wood and the sinuosity of the channel has encouraged the deposition of these alternate gravel bar features. So the flow in this photograph is the same as the flow in this photograph, but you'll see much more physical diversity because the asymmetry in the geometry of the channel. You've got this concentration of flow in this sort of riffle here, this area, this nice scour pool behind the wood structure. So providing far greater biodiversity and also refugia in terms of cover for in-stream species and temperature refugia as well. But it is important that we need to understand that this type of approach is possible. We need to know the river has enough potential for geomorphic work in terms of river, the energy and the flow and sediment supply. So we do this by applying a sediment transfer model. So we built a very, very simple channel here, very simple trapezoidal channel. But we knew when we applied the model that just a moderate flow event would rework the sediment and produce this type of complex morphology here. So we didn't need to build this. We knew that the river would take this initial condition, this relatively simple form, and turn it into this in a relatively short space of time. But that needed an appropriate level of assessment to understand that. So the next site, or what's more typical for most restoration sites, those two sites are relatively constraint-free. So they're not typical of the type of work that we do. More typical, there's more significant constraints to design. So we're unlikely to be working in relatively unimpacted river environments that those last two examples were. So we apply this initial conditions design. There's often much more infrastructure to consider, much more constraints. So this approach means that we basically give the river an initial template that's approximately correct for the imposed conditions, and then let the river processes adjust that to a stable equilibrium form that is optimal for ecological conditions and biodiversity. But because the degree of constraints and risk, often they're much greater than the other types of design approach, it must be based on a systematic science-based design methodology. And I'm giving an example here from the Eddleston Water in the Scottish border. So again, another river that was very heavily canalised about 200 years ago for benefit to agriculture improvements, and also road construction as well. So very little biodiversity in this sort of channel. And like I said, there are quite significant constraints at this site, anthropogenic and natural. Naturally, the river's relatively low gradient, so it isn't of particularly high energy, so it's not going to recover itself in any sort of time scale that was acceptable. And also significant infrastructure and services. There was a water supply pipeline down one of the banks in the floodplain. There's a road quite close to the channel and various bridge crossings. And also agriculture is quite, there's a fair significant amount of agriculture in the catchment we had to be sensitive to. And also flood risk. One objective of the design was we had to try and see if through natural flood management we could reduce flood risk to two downstream areas, or two villages downstream which had flooding problems. So that was another design constraint we had to consider. So we go through this process to develop an appropriate design in this initial design approach. And the Eddleston Water gives a very good example. So this is a LiDAR image of the river as it was, and you can see the river's almost exactly north-south flowing from top to bottom here. But you can see from the LiDAR, and you can pick out the old impression of the sinuous channel. So here we've identified that. And this is a potential new course for the restored channel. So we identify that from the LiDAR, and that gives us an imposed discharge regime and slope. And we need to understand if that's an appropriate channel geometry or channel configuration, because this channel hasn't been in that condition for 200 years. And over that time, there's been significant land use change in the catchment and climate change. So we need to assess whether that general channel alignment is appropriate, and we determined it probably was. And the next thing we do is come up with a very simple channel geometry, so a very simple width and depth for the imposed discharge or flow and slope characteristics. And we use established geomorphic empirical relationships to determine this. So this gives us a very simple geometry that we start the design process with. So we then undertake hydraulic modeling. So we take that simple design and we apply this iterative 2D modeling, 2D hydraulic modeling approach to identify where the design's not working, where the geometry has got to be changed a little bit, and we rerun the model and iterate in that way. And we also progressively add in some complexity design. We add in pools and riffles and other types of geomorphic feature into design until at the end of the process, the final design is this initial condition. So it's this initial condition that we give to the river to then allow it to evolve itself over time to this equilibrium state. So this is the site looking from upstream to downstream. This is the section that, you know, the section that's shown that previous model there. The river used to take this course here, this dashed red line. So it was absolutely dead straight, running exactly north-south for about 4 kilometers. And then the blue line is the reinstated meandering channel that we developed mainly initially from the identification from the old channel from LiDAR. These two, this upstream section and lower section, have been built obviously in the past. This is a sort of a connecting section that was done later. Now, one of the constraints, the design constraints that I mentioned, was agriculture, and you'll see this conspicuously green patch here. So this was a design constraint. This was a field that was sacrosanct to the farmer. He had to keep this field out of the floodplain as much as possible. It was a silage field, very important to him. So our design had to incorporate that as one of our constraints. So here we have a bund. You see this bund here. This protects this field from flooding up to a certain point. Now, you get to a certain size of flood and bits are off. And here you see the site in flood. So here you see the special field here protected. It's under this sort of moderate size of flood. It's entirely dry. So we're meeting that design constraint. But otherwise, there's excellent connection of the river with its floodplains. This provides flood risk benefit by storage of floodwaters in the upper catchment to protect those towns downstream, but also great biodiversity benefit from the reconnection of the river to its floodplain. So this is the site as it was. This is it during construction. This is the same photograph about a couple of years later. So the river has kept the same general course, but it's adjusted it. It's evolved into this more natural state with development of this riffle structure here. This gravel bar features developed and all the associated regeneration of native vegetation. So much improved biodiversity condition as compared to the pre-design state. Now, the final example I want to give is where there's very significant constraint. It's the Mains of Dice site near Aberdeen. So there's a small culverted tributary flowing to the south of the River Don in Aberdeen City in a sort of satellite town called Dice. It's in this area here. It's a highly industrial and urbanized catchment. So a very flashy hydrology and a very constrained site in terms of infrastructure. And of course, the channel was very tightly controlled by housing development. So this area in this photograph here used to be an industrial area, and there was a factory sitting over here. So the river had been culverted underneath the factory, but because of the housing development, the developer wanted to maximize the area for houses. So they daylighted the stream. So they took the stream out of the culvert, but pushed it right to the edge of the site. And in doing so, they produced an unnaturally high channel slope. It went right down the steepest part of the ground here. And this provides a really good example. The initial construction of this channel, which we had nothing to do with, I'll hasten to add, was a very good example of a lack of consideration of appropriate geomorphic design, because this is initially what they built. A narrow channel confined within these deep banks, cutting through unconsolidated sediment. And, we knew immediately this was a very risky channel. It wasn't stable. Given there was going to be houses built just to the right of this channel, this just was never going to be stable. The contractor didn't agree with us, just wanted to keep this channel. And so, just through poetic justice, there was a flood event about a week later, and the channel ended up looking like this. So, there's been a head cut. There's erosion started at the bottom here and worked its way all the way upstream. There's a bit of a waterfall structure here, and all this material is gone. You can see it's obviously an entirely unstable site now, not appropriate for a channel adjacent to housing. So we had to go through this design process. So following the nature-based approach, although we're really constrained in terms of what we could do, we couldn't really let the river do its own thing. We do apply the nature-based approach by reproducing the natural morphology of a channel, a stable channel, under the imposed condition of such a high slope. So where you've got greater than 3% slope, in nature you have these step pool channels. This is the optimal way that rivers expend their energy in terms of morphology. So this is in nature what a step pool channel looks like. So you get these boulder steps separated by these pools, and this is what we try to reproduce. So this is an empirical relationship based on natural channels that we use as to develop the longitudinal design profile for the channel. So H is the height of the step, L is the spacing between steps, multiplied by the general bed slope, related to this constant which varies between 1 and 2. So this is the design criteria we use to try and make sure that our design replicates natural channels. And we produce this in cross section. This is the, or long section rather, this is the design we produce, obviously exaggerated in the vertical. And to make sure, because of the degree of constraint, we had to make sure the structure was going to be stable. So we ran a hydraulic model to make sure that these steps were going to be stable under a high flow, a very significant flood. Was modeled to make sure that the particles, the boulders that make up the steps, weren't going to move. So we engineered or designed the channel to be able to withstand this type of extreme flood event. We produced a series of designs, given them to contractor, and this is a design built. So you see what we've done is, although we're constrained in space, we've managed to open up the bed of widen the bed of the channel. So we've got this sort of low flow area here, but on either side we've got these sort of cobble sediment benches. So under high flow, the high flow is distributed over a wider area, so there's less force on the bed. But also, here's the sequence of steps. A sequence of steps running down through the channel, and the energy is expended by the turbulence forces as the water flows over the steps. This is the site again after a couple of years. This is the photograph of looking upstream on the site before the flood event, and already you can see there's been some erosion even at this low flow. So we knew this wasn't going to be stable. Look at the sort of size of sediment it's cut into. This is it looking upstream after the flood event, and you can see the head cut and the waterfall of the limit of the head cut up there. This is it immediately after construction with a series of steps and these cobble benches. This is it shortly after construction, or a year or so after construction. This is it more recently. So it's really interesting. You see the risk. I mean, this is one of the houses up here. There was a real significant risk to this. We had to make sure this was stable, and it is now stable. The bank's really stabilized up with vegetation. None of the steps have moved, although because we incorporated natural channel form in the design, there actually has been some adjustment of the channel. So the channel's been able to adjust its form by moving these cobble benches around to a more natural equilibrium state. So the channel has, because we've incorporated process in the design, it has been able to adjust and refine its morphology to be optimal for energy expenditure. So this channel has now experienced much bigger flood events than caused the erosion in the first place, and is entirely stable. So, a really good example how applying this nature-based approach and reproducing natural channel form works very effectively. So the last thing I want to very quickly speak about is other methods of river management or river engineering. So we're often asked to come up with solutions to protect infrastructure in a river that's behaving in a dynamic way. So typically, and it's not everything we do, but I'm going to give us one example of sustainable bank protection. Typically, traditional protection of bank is using large rock or concrete or walls. Structures like riprap, rock revetment, boulder placement. So this is what's typically used, and there's better ways of doing it. I mean, this type of approach isn't natural or sustainable. There's a large carbon footprint associated with it. there's no biodiversity benefit. There's a biodiversity loss as a result of putting rock in a bank. And it also is not very effective. These often fail. Because they're static, they become undermined and are outflanked. And also they don't, all they tend to do is to, they deflect the energy of the river to the next unprotected section of banks. At best, all you're doing is moving the problem to somewhere else. So there are alternative approaches. This is an example of a traditional method that failed. This is a river in the Cairngorm Mountains. There'd been a big flood event. This is the eroding bank here, impacting these holiday chalets. So the owner of the chalets just got a building contractor in, and a great cost put in this wall, boulder bank protection. These boulders are about a ton in weight, each of them. But it's not very effective in this type of environment. Very dynamic system draining from the Cairngorm Mountains, very upland system. So where you get this type of feature, this large gravel bar developing, it's forcing the flow to the opposite bank, why the erosion happened in the first place. But because there's rocks in here, the river can't physically pick up that rock and move it. The energy that the river's trying to expend isn't expended by the channel migrating laterally, but it'll erode the bed vertically. And you see this sort of deep channel sort of developing here now. And if you go downstream, sure enough, this channel's deepened sufficiently to undermine these boulders, which fall into the channel, and then the river gets in behind, and over time, this is really unraveled. This has become a really unstable site, and these chalets are a risk again. Another example here is the Eddleston Water, where this, same idea, there's rocks being undermined and falling in. And even where we're using, this is in Yorkshire, sheet piling being used, same process again. You've got a gravel bar developing here, pushing flow to the outer bank, undermines the sheet piling, which falls over, which is meant to protect this golf course in the background. They've had to put in more ad hoc sort of boulders. So these traditional methods just don't work, and especially in dynamic river systems. So the alternative there's many alternatives, but one which we often apply is large wood structures. These are sections of tree, sections of trunk, maybe 5 or 6 meters long, with importantly the root plate still attached. So they're a natural material, and it's reproducing how banks naturally stabilize. It's the process by which banks or rivers naturally mediate their erosion rates. And they're more effective at energy dissipation. They don't just deflect the energy to the next bit of bank, because of the root structures that we put into the bank, because of their complex structure and the turbulence processes associated with them. They actively dissipate energies. They're actively protecting. They're not just bouncing the energy off elsewhere. They're actively dissipating the energy. And they're also plastic. I don't mean they're made of plastic, obviously they're made of wood, but they're plastic in the sense that they deform and adjust as channel shape evolves. So they're working with every process. There's a degree of adjustment allowed, so that they're not just these static features that get undermined and outflanked. They evolve with the channel to some degree. They're generally cheaper to implement and maintain, often half the price of an equivalent large rock structure, and significant biodiversity and carbon benefit gains as well, because you're using natural materials, you're encouraging natural revegetation of the banks, and also more agreeable to regulators. In the UK, at least, there's regulators, environmental regulators are very keen to see these types of approach be applied, mainly because of these reasons above. Like I say, there's other types of sustainable, sometimes using large wood structures is not an option. Often you can't source the wood, or there's space constraints. So there's other types of sustainable nature-based bank protection methods I can describe if need be, but this is just one example I want to focus on. So this is what they tend to look like. So in cross section, so this is the previous eroding section of bank. So we'll reprofile the bank, we'll take all this material away, dig this material away, we'll put in these lengths of tree, about 5 or 6 meters long typically, with the root plate presented to the flow in the bank. This is a 2-tier structure. So there's one tree at sort of into the lower than the bed level of the channel, and one above it, and they're set into this foundation of cobble and gravel sized material, which is quite important. There is some rock used. We use natural rock to provide ballast and stabilization to the wood, because you don't want the wood floating off, as wood often does. And then we reprofile the bank to this more stable angle, about a 2 or 1 in 3 angle really. And then when we've removed the material from the original bank, we retain the turfs and replace them immediately onto the bank, so we don't have a bare earth surface that was easily erodable subsequent to the works. And also we try and plant native tree species in here as well, because their root systems really provide an excellent binding of the bank to provide protection. So the example I want to give of this bank protection measure is on the Andakilsa River, which is near a place called Borgarnes in Western Iceland. It's in this location here. So it's a river system that is not a glacial system, it's a non-glacial system, but it's developed for hydropower, which is part of the problem. The hydropower is actually one of the major causes of the bank erosion in the first place. Here's the powerhouse of the hydropower scheme, and the specific site is here. This aerial photograph shows the extent of the bank erosion. The bank erosion extended from here down to here. Now this is a geothermal pipeline, so a bit of infrastructure that had to be protected, and one of the reasons why the bank protection was important and was required. So we've got to protect this, at all costs, protect this geothermal pipeline. This here is a pile of large boulders that had originally been proposed for a traditional hard bank protection design across here. So we managed to persuade the owner of the power company, or the power company were going to implement this, that there's a better way of doing it, a more sustainable way of doing it, which they were very keen to do. They're very keen to try new nature-based approaches. So here's the site as it was eroding. Here's the powerhouse from the hydropower scheme here. This is a little bit deceptive. This bank is actually about 4 meters high, and it's about 4 meters depth down to the base of the river. So very significant bank erosion. It migrated, since the erosion started, it migrated about 50 meters over to the right here. And this is the materials we're using. So this is the large wood. This is the trunk structure with the root plate intact. There's a number of them here. These are the boulders that we're using for the ballast to hold the structures in place. And in the background here is a pile of this gravel cobble material that's used for the foundation material for the structure. So here we see the works going in. This is a sort of nice real world cross section of the design. So here's the lower tier of trees below bed level with the trunks running into the bank here. Here's the second tier up here. Here's the sort of gravel cobble foundation material that they're set into, and then the boulders that are providing the ballast to hold them in place. And then there's the reprofiled soil. And once that's been done, we reinstate here's all the turfs stored up here. And this is the turfs. This is about 3 or 4 months later. We've got this reprofile bank with a stable angle. The turfs have really taken off. They're growing well. And we also, really luckily, the landowner was willing to give us these juvenile trees that were sitting in behind the bank here. And we could take those, we could dig the whole root structure up with the construction machinery and just transpose them directly into the bank. So immediately their roots are growing and providing this binding structure to the bank, which is a really excellent way for kickstarting this natural regen. So this bank has now experienced the biggest flood in 20 years that would normally have caused the migration to move another 5 meters, but there's been no erosion whatsoever. So a very effective design that we're really, really, really happy about. So yeah, that's really very quickly me running through these examples of nature-based approaches. Many other examples I could have given. I've had to remove a few of them from this talk just because of time constraints, but the take-home points really are quite general. An important one, I think I've demonstrated that detailed understanding of physical river processes is key to identifying the correct approach for nature-based designs. We've got to understand the river before we apply the appropriate design. And the fundamental philosophy really is reproducing natural river form and process. This is the most effective and sustainable design strategy. It's the river knows best as to how to produce a stable form, and also for biodiversity. So we really try and reproduce these natural processes as much as we can, these fundamental processes. And again, different types of approach are required in different environments, and this is why we do the necessary level of assessment. We need to understand the type of approach that's required in different environments. And again, looking back to the Mains of Dice case study, that sort of case study next to the housing development, it's always, regardless of the degree of constraint and the scale of the site and the footprint of the site you've got, it's always possible to reproduce natural process. There's always we're always able to reinstate some natural form, and that provides a more stable design, but also allows the channel to have a have the potential for some biodiversity gain as well. We're allowing the river to adjust itself over time. Even the most constrained site, a little bit of adjustment provides biodiversity benefits. So there's always the option of we don't need really heavily engineered channels in constrained sites. We can still reproduce natural process and form. But especially where there's significant constraints, a design methodology needs to be theoretically and evidence-based, and may, depending on the degree of constraint, may need some really detailed assessments. An example I've given, hydraulic modeling or sediment transfer modeling. These types of approaches are really essential just to ensuring that we've applied due diligence in coming up with a design that's appropriate for the site and is addressing the constraints. And a really important point, I think this is one of the main reasons that traditional river engineering doesn't really work, or there's many examples of it failing, is that rivers change. We don't want to fossilize rivers and fix rivers. We can't do that. If we don't incorporate the ability for dynamic behavior, a design's not going to work. So we need to explicitly incorporate the potential for dynamic behavior and physical change into our design process. And that's really important. And often it's simply a case of giving the river a bit more space. That's often what's needed, just giving the river a little bit of space to adjust. And that allows for dynamic process. And also obviously incorporating these nature-based approaches of reinstating natural channel form and process. And all of these tenets here, all they're really doing, all we're trying to do in the work that we deliver is managing risk. So this is managing risk as really considering constraints. We need to make sure that the constraints are paid attention to, and the risks that are associated with them are managed. And we do this by applying these sort of approaches. And I think, yeah, that's my talk.
Thank you very much, Hamish. Very clear exposition, wonderful slides and all that. We actually have so far 11 questions that have been submitted, and which I've taken down. People can, as you're answering, people can still submit questions. I'll try to keep up. The first question, actually the first two questions, come from Mike Potter. And I'll read it off. As part of the STF Pickering, we had a full meeting on natural capital, aka ecosystem services. It turned out to be very thought-provoking. While I wholly agree with the danger of greenwashing and the cost of everything and the value of nothing, do you think there is a genuine case for assessing the value of natural processes in providing the evidence to make them happen? That's the first question.
Yeah, I mean, most of my work is involved in this practical design, but we did do a project. It's related to the bank protection project I just showed in Iceland. So as a more catchment-based, like I said before, the bank erosion problem is related to the hydropower development. I mean, basically the upstream of the powerhouse, there's a reservoir and it's impounding all of the sediment that would normally be transported downstream, and we need to understand a way to sort of reinstate that sediment back into the downstream river to have a more natural river environment. I mean, the river's much more able to erode its banks when it doesn't have that sediment to transport, dissipating that energy that it has. So, but one we looked at that was to look at various methods of reinstating a natural sediment transport regime in the system, and we looked at a number of options, which were sort of retrofitting the hydropower dam to allow sediment to go past. Another option was just simply removing sediment from the reservoir and just trucking it downstream. And another option was looking at upstream land management, because there's very significant land management problems upstream, which result in excessively high sediment loads coming into the reservoir. And we did a cost benefit analysis, which was quite specific. Now, I didn't do it myself. It was an environmental economist did it. But we looked at these options in terms of looking at the value, you know, well, there's Icelandic kroner value of these different options, and trying to take into account all factors and looking at timescales going from 10 years to 100 years of these cumulative benefits. So yeah, there's definitely a way to factor in economic considerations in this sort of thing. And that was really interesting, that assessment, because it determined that by far the greatest benefit longer term was for doing the upstream land management. That was by far the most effective, cost-effective measure, taking into all considerations in terms of, you know, things like the physical benefit and the benefit to the functionality of the hydropower scheme, but also socio-economic benefit and, you know, quality of life for people living upstream, all that sort of thing. So yeah, these things can be given a value to them.
Thank you. The second question again from Mike Potter. In terms of the Alt-Lorgi project, what impact did the works have on agriculture, given that the 1980s work was performed on that basis? It doesn't look like BMV land to me. Has the economic viability of productive land changed in line with subsidies or lack thereof?
Well, that site was really constraint-free, because despite them having done those works to try and improve agricultural productivity, the land, you know, still remained very, very unproductive. So the work that they did wasn't really very effective, and the land couldn't really be used for anything other than sort of rough grazing for cattle. It was a very poor value. So, you know, that didn't really need to be taken into account. It was, you know, even before the project occurred, the land was, you know, dormant. You know, it was redundant in terms of agriculture. So for that specific project, we didn't have to do any assessment like that. But in other projects where we're doing, you know, projects where there's more significant agricultural constraint, we do have to take into those accounts. You know, we're designers, we don't do that specifically ourselves. I mean, when these projects get prioritized for implementation, there's a stage before that where the regulator will do these sort of assessments and determine if, you know, the benefit to the natural environment outweighs the impact to agriculture.
The third question comes from Sebastian Burke. In the MERLIN project, we try to monitor the restoration effects for various aspects relevant in the European Green Deal, such as green growth, zero pollution ambitions, flood and drought mitigation, health and well-being. Is that obvious to you, or are we overstretching the ambition of restoration with this? Yeah, I believe that's.
I mean, some of these things are, I mean, these projects I've shown, and other projects, they're very good case studies, and they're monitored to determine these sort of benefits. I mean, the monitoring does tend to be a bit more specific in terms of we can quite easily monitor, well, with appropriate instrumentation, we can monitor flood risk benefit, and we can model flood risk benefit. We can, you know, do ecological assessments to understand the ecological benefit of the scheme. And that's typically what we've got involved with. We haven't got involved in broader implications of this type of work. We tend to look at, for specific types of scheme, what are the flood risk benefits, you know, what are the rates of physical evolution of the site. We've looked at factors like, you know, how important is the large wood to implement? Is it critical to realizing the physical and ecological benefit? We do a lot of work on, well, in combination with other associates, we'll do, you know, in-stream and sort of terrestrial ecological assessments to see how the sites evolve. So we tend to be focused much more on those sort of site-specific issues that we then, we use as sort of validation of this type of approach. So if we're applying a certain type of restoration design, we'll use the information from a previous monitored example to show to stakeholders that these things have, these measures have a real, practical, measurable advantage post-implementation.
The fourth question, from the Edelston site, in balancing design constraints at the outset, is there any consideration to encouraging experiments in alternative agriculture, such as wet meadows for grazing? You had to protect that silage field. Or is that constraint absolute?
Well, yeah, the issue, that specific issue was a very specific requirement by the farmer. And these sites, one of the biggest practical constraints of getting these works done is getting agreement from landowners to do it. And it took a lot of effort in the Edelston Water to get this work underway. We didn't really lead that. There was an NGO, the Tweed Forum, who were really good at sort of liaising with all the landowners and explain to them what the potential benefits would be and what the compensation mechanisms might be. But there was no real interest initially in doing the work. We initially did a whole assessment of the entire catchment, and we prioritized the areas that really needed restoration work done first. But none of them got done first. What happened was there was it wasn't a farmer, it was a guy who owned a bit of land. He was like a lawyer from Edinburgh, owned a bit of land in the middle of the site, and he wasn't interested in agriculture. And he said, yeah, off, go and do it. And that sort of created a bit of a domino effect. So then all the other landowners wanted a bit of the action, and before you knew it, you had an entire 5 kilometers of river restored. So getting the landowner buy-in is super important, and to do that you have to bargain with them. There's always a negotiation, especially if it's a farmer. There has to be something in it for them. It's rarely a completely they're not just offering up their land just for the benefit of the environment. I think there's always got to be something in it for them. But in terms of alternative uses of the land, that would be something that's almost certainly, in fact, I know that it was discussed in other areas. The Tweed Forum led those discussions with farmers, but we weren't really involved in those sort of discussions. We were just told what the constraints were for the site, and we had to design on that basis.
The fifth question comes from Kiran. How have benefits of NFM been measures in terms of 1, improved biodiversity, 2, reduced flood risk?
Well, in the Edelston Water is a good example because we've just done the design work and helped in the construction implementation, but there's a really big project. The Edelston Water project's a big project, and there's quite a lot of literature out there on the Edelston project, and it's a project it's led by Dundee University, and it's been going for over 10 years now. So very, it's not just the restoration works we've done, it's other works throughout the catchment in terms of replanting and creating wetland areas and all these sort of things. So there's a lot of work done in terms of there's gauging stations being put in, so there's a lot of monitor equipment going in to measure the the NFM benefit of the works that have gone in and the trajectory of that over time. Similarly, in terms of the biodiversity benefit, there's a lot of work done in terms of there's a lot of sampling sites that are distributed through the catchment, where the monitoring sites that are used for as locations where with baseline data from before the works were done and then repeat samplings done. So it's not just biodiversity. I mean, there's the physical diversity, there's repeat surveys of the physical condition of the river and the associated biological signal with that. So there is the Ayleston Water is a really good example of where that's been done, but it's quite unique. It was set up as a test catchment, so it's quite unique on that basis. Not all of our sites have that opportunity, and still monitoring is one of these areas which is lacking in these projects. And we really need, good exemplar projects to be used as case studies to allow monitoring to demonstrate how effective or otherwise these objectives can be. But every site that we have monitored, we've been able to, a small individual restoration measure, say if it's even a kilometre section of river, is quite a minimal flood risk benefit improvement, because that sort of scale of intervention just can't deliver a silver bullet for flooding downstream. So, but even incrementally, you can see, okay, this one measure, allowed a sort of 1% reduction in flood peak and a delay of the flood peak by half an hour. So you can scale that up. You can say, well, if we applied this much more widespread to the catchment, then we'd have a really significant benefit. So the individual measures, we're not at the point yet where we're implementing enough NFM to really show a significant benefit downstream, but you can see how these individual measures done in sort of series and in parallel could realize a very significant benefit. And we do this through, we demonstrate the benefit through modelling and through monitoring. And like I say, there's a lot of other monitoring that's done in some of our sites. A sort of small subset of our sites are monitored in terms of, indices of biodiversity and physical diversity.
I'm going to skip to the 7th because it seems related. Again, from Kieran, what consents are required in order to implement NFM measures, i.e. Natura assessments, planning, etc.?
That's a good question. In Scotland at the moment, it's a bit of a grey area whether planning consent, like planning, you need to go through a planning application process. Some projects do, some projects don't, and it's a sort of slightly subjective decision if it needs it or not. But any in-river works, the consents need to come from our, environmental regulator, SEPA, Scottish Environment Protection Agency. They need to approve any works before they're implemented, just in terms of, risk to water environment and ensuring that the designs are appropriate. So that's sort of two levels, over and above obviously getting a landowner to agree to the works. The planning permission from the local authority may or may not be required, but we always need approval from SEPA, who will consult, so that their approval will incorporate opinions from other organisations like the salmon fishery boards, rivers trusts, in Scotland we've got our environmental nature regulator is the Nature Scot, so they would also advise on protected species and that sort of thing as well. But there's effectively two levels of approval that are needed, potentially just one.
The next question comes from Mike Potter. Is the Scottish planning system really so unsuitable for purpose as to allow planning for development without any sensible consideration of this channel? This is the case of the Aberdeen one.
Yeah, that was quite a few years ago. Without being libelous, I would question some of Aberdeen City Council's decisions on planning in relation to the water environment, and I'll leave it there. But yeah, I mean, they're learning all the time. They do take advice from SEPA. Like I say, the Mains of Dye site was 10 years ago now, so things have changed, and not necessarily for the better, but they have changed. So yeah, I mean, the reason that we got involved in that project is because the the designs for the site, the drainage for the site had gone through, not so much the planning authority, they'd gone past SEPA, and SEPA had immediately raised concerns. The developer objected, saying, well, I've dug these ditches for years and I know what I'm doing, there's no problem here. So SEPA contracted us initially just to advise on whether the design was appropriate, and immediately you could tell it wasn't appropriate. But SEPA they didn't have much, they didn't want to, I think, ruffle feathers too much at the time. So, although we said that this channel was really risky, they didn't sort of mandate that the contractor had to modify the design until the flood happened, which is sort of after the fact. But it required that flood to happen before there was an agreement. Actually, to be fair, once the flood happened, the contractor said, he held his hands up and said, right, yes, absolutely, please fix this. So he didn't need approval from SEPA. He was happy to go with our design.
Jan, you were muted.
Sorry. The next question comes from N. Thornton, and that is, do you design the planting of riparian woodland into your schemes? How would you monitor the impacts of riparian woodland on geomorphic processes?
Yeah, it's for instance, when we implement large wood bank protection, it's really a intermediate protection. And by intermediate, I mean, for as long as the wood, is until it decays in the bank, which might be, 20 to 50 years, and it's providing protection. But that's not the time scale. We need to look at the longer time scale. So one of the objectives of the project is, it has to be sustainable. So that's why we promote the planting, or one of the reasons we promote the planting of riparian vegetation is that after the effect of the wood that we put into the bank is removed over time as it decays, we've got a fresh supply of natural wood coming to the river that will naturally protect banks. That's the method, or the means by which a river mediates this bank erosion, is by trees coming in and naturally aligning themselves along the bank and getting trapped and stabilized there. And so that's the process we're trying to develop. So that's how, one of the practical ways that that the riparian vegetation is going to work. And also would come into the channel. And we, for the restoration benefit, we'll put these artificial structures in to kickstart that process. But as we regenerate the riparian corridor with trees, we want trees to come in naturally and do that natural job of wood supply, adding to the river and adding that complexity. So that's the processes we're trying to reproduce. And you can see in a few of our sites that's working very effectively. Now in the Allargy, we've put the wood in artificially, but 10 years later, the more dynamic character of the channel, and it's moving around its floodplain a lot more, it's naturally incorporating wood into the channel now. So that wood's having the same effect, but in a natural way. So we've sort of closed the circle in terms of those processes, which is really encouraging. It does work. It's quite a dynamic system, but it will work over time. Yeah, I can't remember the full what the full question was, but I hope that answers it at least partly. We don't do we do planting schemes, but we often have some. Often the landowner, in conjunction with an associate of ours, will identify the appropriate species and densities of planting. We will generally specify the areas should be planted. For flood risk management, also a rougher floodplain provides greater residence times of water in the floodplain. So we'll suggest a level of density of planting to realize that level of resistance or roughness in the floodplain. But otherwise, the planting plan is, an appropriate density in combination with a good mix of native species that would naturally be there. Often to allow the natural regen on the Lorgy, we had to really fence off the whole area. There's a very high deer population there that meant that any saplings were getting munched pretty quickly. So we fenced, as soon as you fenced the area off, was a lot of planting done, but the planting didn't really take. It's natural seed establishment that provide the regen in the end, and it's worked very effectively. As soon as you got the deer off, it came back. But there is a problem that a natural environment has a certain density of grazers. If you have no grazers, you end up in an environment that's just like an overly thick canopy that has problems, other problems. You need to identify an appropriate level of grazing for that environment. And it's quite hard to do. It's quite hard to get that right. And it's really, in Scotland, it's really about trying to get deer numbers right down, get deer densities down to a natural level, which is quite hard because it involves a lot of shooting of them, which is not very sustainable. But yeah, hopefully that's answered that question.
The next question is from Joshua Reut. How do you plan for future maintenance work as the natural structures decompose, or will the site self-stabilize by then, 20 to 30 years from now?
Sorry, yeah, like my last question. I mean, we do what we want to do with nature-based designs. They're meant to be sustainable, so we really don't want to go in and manage. As much as possible, we want to have a sort of self-regulating environment there. So we want, after 20, 30, 50 years, when these road structures decay, we want the re-established riparian corridor to provide the wood that naturally stabilizes. I mean, there's always going to be locations where you might have to do a bit of adaptive management to these designs, but you want to absolutely minimize that. And that's the whole point of one of the objectives of the approach is to have a more sustainable management approach.
The next question is from Bill Blackledge. The Iceland example, the bank is stabilized, but doesn't that push the energy effects upstream or downstream?
No, because the bank is much rougher now. It's rougher because of the wood structures comprise the bank protection itself, but also the roughness which is developing from the re-establishment of the native tree cover on that slope. So the banks is much, much rougher than it was. So there will be some translation of energy, but massively reduced compared to a rock structure. We've actually done some modeling on this. We've done some modeling on, how much the forces acting on the bank are reduced as a result of the roughness of these structures compared to, the wood structures compared to a rock structure. I can't remember the numbers right now, but it was, a significant amount. I mean, the amount of, energy expenditure or energy, the sort of dissipation was, we compared to the traditional rock structure is about 4 times more, something like that. I can't remember the exact numbers, but we have that. We did some R&D work on that just to help justify this type of approach when it came to these sort of technical questions.
We're down to the last 2 questions. Joshua Reut asks, in the case of the Aberdeen example and others, is it possible to bring a downcut incised channel back up to the floodplain elevation? Perhaps south of Aberdeen, you didn't control enough of the site up or downstream to do that, or have the resources for that much earthwork?
With that site, no, because it's a completely unnatural alignment of the channel. And you've got a fixed elevation upstream where it comes out of a culvert, and a fixed elevation downstream where it goes back into a culvert under a road. So if you draw a straight line between the two, the channel bed has got to be a certain elevation below the floodplain. So it can't really build up because it's got to get back out the bottom again under another culvert. So under that condition, no. But where there is the opportunity to do that, we do try and do that. We do try and create a sort of 2-stage channel, like an inset floodplain with a lot of roughness on it that encourages accumulation of sediment over time, which will bring that inset floodplain and channel back up to the level of the prevailing flood elevation. But it wouldn't have been, very rarely do we actually have the opportunity to do that, because almost always in a river system, the river systems that we're working in, they're quite, even in agricultural areas, they're quite developed. So you will have an upstream and downstream bridge typically, which will mean that the inverts of the bridge or the river at the bridge are fixed points. So you can't do much about that. We're working on a project now in Aberdeenshire where we have that exact problem. The downstream limit of our site is a bridge, and it's got a, there's the invert on the apron of the bridge, and we just have to design to that. We can't allow the river's really incised below its floodplain. We should really be bringing it up into its floodplain, but we're not able to do that just because of that fixed point downstream.
Before I say the last question, I want to make sure I don't forget to announce that the next webinar will be on the 3rd of April. It'll be a presentation by Tom Boussier of the Deltaris Group in the Netherlands on insights on MERLIN case study work. So the last question is from Declan Ahern. He says, a fantastic presentation. Can you explain what was meant by external, extremal hypotheses relationships? I'm not sure I'm reading that right.
No, that's correct. That is well, I'm not wanting to go into too much geomorphic, fluvial geomorphology theory here, but relationships which define the optimal sediment transport rate of systems. Often one theory about developing a stable channel is that you want to maximize sediment transport rates. So that's where the extremal comes in. You're trying to develop a channel form that maximizes the potential for sediment transport. And that's just one empirical type of relationship that you use to come up with an initial stable channel design. There's simpler ones. I mean, the more simple empirical, like hydraulic geometry relationships, are actually easier to use, and they're a very good starting point because you refine that. It never produces the final design. It just gives an initial rough geometry that you then use the detailed 2D modeling to refine and come up with a much more defendable geometry. So, but it's just one example of a type of fluvial geomorphology relationship that you would use to try and come up with an initial candidate channel geometry.
So that, I think, brings to a close all the questions that were submitted. I take the luxury of just extending a special thanks to Hamish for an excellent presentation, as most of the people leaving left said thank you very much. I appreciate very much your taking the time and putting such a great presentation together. I turn it over now to Jörg. Jörg, you're somehow muted.
Wrong input. So yeah, just want to say thank you from my side. It was an excellent presentation, very nice examples. Thanks for being here. And maybe Astrid can tell us the next webinar.
Yeah, Jan already indicated that it will be something MERLIN internally, so working with the self-assessment, the ISN self-assessment tool in relation to MERLIN case studies. The detailed title will be on the website very soon. And it's Tom Pauser from Deltaris who will be speaking. Thanks, Hamish, also from my side for this.
Thanks very much for having me. It was really good to talk about these things, and I really like the questions. Some are a bit beyond my involvement in these projects, but it's good to think about these questions myself, and I can think about them after this meeting now and see if I've got people I can speak to about these questions that are quite important, obviously. So, but thanks very much. I've got to jump into another meeting now, unfortunately, so I better rush off. So thanks very much.
Okay.
Thank you.
Thanks everyone. Bye bye.
Bye.